Morning, everyone. So we're about halfway through this energetics chapter. I just want to give you a quick overview as we continue on with today's new lesson as well. So far this chapter, we've been looking at a guy called enthalpy change. Enthalpy, we've been using the letter H for it. Enthalpy, it's very similar to energy, but it's specifically looking at the heat type of energy, and it's specifically looking at the heat inside the system. For us in chemistry here, the system would just be the particles. It could be kinetic energy, could be potential energy and whatnot. Whatever sort of amounts to heat, we want to be able to track the enthalpy change as we go generally from reactants to products, right? So whenever we see change, in physics you can just go change is final minus initial. In our case here, because our final condition will always be what we produce is called products, we can actually write this down here. We're interested in the delta H. The delta H is actually going to be the enthalpy of products minus enthalpy of reactants. If I plot this on an energy level graph here, you're going to be able to see we're plotting enthalpy. It could be against reaction, it could be against time. We could have, let's say, an endothermic reaction. Although I may not know necessarily how much energy my reactants have, nor how much energy my products have, I can figure out over the course of the reaction, have I, in this case here, gained energy as particles, or have I lost energy overall? In this case here, if I just sort of extend the reactant line over, if I point towards the product, an arrow that points upwards means our change this time is positive. And in this case, so far we've been looking just at enthalpy changes. Positive enthalpy change means it's endothermic. It means whatever the heat term is going to be actually on the reactant side. I would put a plus energy or plus heat term on the left-hand side. That would then imply that the reactants started off with a certain amount of energy. They stole a bunch of energy that wasn't his, and as they become products and different chemicals, they store all the energy inside the bonds, and therefore my chemicals are now at a higher energy. Couple important notes here is the system is always the particle nature. The system is always too microscopic, so any description of any temperature changes here always imply that we're surroundings. We imply that we do the opposite. If in this case here my system gained energy, it's because it stole energy from me. The temperature will actually cool down. So it's clearer if they say surrounding, but they can just say the temperature here decreases. We tend to lose that temperature. It's like my hand outside that test tube here. As I hold that test tube from the outside, as the particles themselves are stealing the energy away from my hand, I end up feeling cold. So we are always macroscopic. Even we did the example of us, if I put my finger into this test tube here, the particles are still going to react around my finger. It's still going to steal heat away from my finger. I'm going to still feel cold no matter I hold it from the outside or even touch it from the inside. So we are interested in finding this guy here called delta H. Not just in this case here so far I've said positive is endo, negative actually means exo. We actually are interested in, as we actually perform each particular reaction, how much energy is actually given off per mole. So if I run this statement once, I want to figure out, so this one here absorbs energy, but per mole does it absorb 10 kilojoules or 100 kilojoules? I want to get a sense of how much energy actually gets absorbed. So this sort of introduces sort of the first main section of this chapter. We're going to learn in total 7 different ways of finding this delta H. And just keep in mind, delta H is always the enthalpy as a product minus the enthalpy of reactants. It's just that when we actually get to some of these other methods, sometimes the formula switches. Sometimes it's like, oh, use the reactant numbers first minus the product number here. But nonetheless, by doing the formula as written, it still figures out your energy at the end of the day minus the energy at the beginning. So just keep that in the back of your mind as we go through this here. Let me just summarize for you the 4 different ways that we've done so far. First way was calorimetry. Calorimetry was our experimental method. That part there just sort of summed up as, to find the delta H something, we had to use the MC delta T to convert what my thermometer says as a temperature change. M is the mass, usually of water. C is 4.18. Again, usually pretend it's dilute, even if there are chemicals there. We flip the sign because the system is opposite the surroundings, and then we have to divide it by mole so that it's not specific to just that exact experiment that I did, but then I get a kilojoules per mole every time I run that equation. So if I'm given experimental numbers here, calorimetry is the way to go. Second method here was called bond enthalpy. It was, in general, bonds store energy, different bonds, different combinations store different amounts of energy. If I can compare how much energy I input to break bonds minus how much I output to form bonds, I should be able to get some overall energy change over the course of the reaction. So in that case there, the formula was delta H. We use bond enthalpies here. I'm going to give you a summary chart later on that has all of this one here. Here, the formula actually switched to, use the reactant, let's break the bonds, sometimes we say broken minus formed, use the reactant ones first and the products ones afterwards, but that still calculates for you the enthalpy of products minus the enthalpy of reactants. It still gives you, based on our convention, in the forward direction, are we end or exo? It's just that when we use these numbers, it's actually going to be reactants minus products for the sign to come out correctly. The math is not overly hard in this section. It's just going to be simple pluses and simple minuses. Make sure in case you have multiple, let's say in this case you have many products, make sure you distribute that minus over, or just type in the whole, all these bond enthalpies of products and then subtract it all as one entire number. The third one here is probably the most important, which was called Hess's Law. We saw that it works, but unfortunately here it's very tedious. This one here, as I introduced it to you, is basically a statement of energy conservation. Your reaction might take place over many mini steps. Each of these mini steps here might have their own delta H's that I already know. And then what we did is we played around with, if I scaled the equation, if I doubled the equation, we scale delta H. If I had to reverse the equation, if I had to flip the equation, the delta H flips sign. So if it was endo one way, it's now exo the other way. And overall, if I have the same start and the same ending position, if I end up adding a bunch of the equations in the mechanism, I end up having to add delta H's. Those are the ones, sort of manipulations I can do. I want to have same start, same finish, and conservation energy, Hess's Law tells me that regardless of the route, the energy is always conserved regardless of that path. We call functions like that state functions. We saw that that worked, but it was very tedious. So in number 4 here, yesterday we introduced formation numbers. We defined what a formation was. Formation was the making of a 1 mole of the compound from just the pure elements in their standard state. Somehow by defining the formation, these numbers here, tabulating a bunch of heats of formation, somehow in the background it would have done this part for you, and all we're having to do is, if I'm interested in finding the delta H, I would just add up all the heats of formation, and we saw from the enthalpy cycle here, products minus reactants. So now we have 4 different methods here. Depending on sort of what detail and what data that they give you per question, you might have enough. If it's experimental, right, you can do calorimetry. Bond enthalpy is a good start, but the limitations there are bond enthalpy has to be gaseous and it has to be averaged over a bunch of compounds. So averages are nice because they apply to everything, but it's also not nice because it doesn't apply to any specific compound. Formation numbers here were good, right? If I happen to have the formation numbers on table number 12, I can just operate on them and I can figure out the delta H. Today's lesson will feel very similar to yesterday's lesson. We're going to talk about combustion as another shortcut for Hess's Law. So we're going to start here. Let's call that method number 5. I'm going to first sort of qualify for you what it takes in this chapter here to be a combustion reaction. What are some of the details there? And then like yesterday, we're going to look at the enthalpy cycle. We're going to come up with an expression like this so that if I tabulate a bunch of combustion numbers for you, they're actually all tabulated for you on table 13. We'll see later on. How can I find the delta H of any reaction based on the enthalpy cycle? So if you just sort of think about yesterday's lesson here, it should feel very, very similar. The nice thing about a combustion reaction here is we actually have a lot of familiarity with it already. So what is a combustion reaction? A combustion reaction here involves we are burning 1 mole. Again, I want to keep emphasizing there's this pesky little 1 mole in the definition. You have to include it because I want delta H's to always be quoted per mole. So later on, if I have 5 moles of reaction, I can just scale up the guaranteed 1 mole value by 5. So burning of 1 mole of your species, right? It could be an element, it could be a compound. Usually they do specify here in excess oxygen. We want the fire to be raging really well. We don't want them to have any limiting excess kind of questions. In the case of excess oxygen, that sort of implies to us that the combustion will be complete. So we had always predicted complete combustion. If the burning goes fully oxidizing with the oxygen, well, we're going to end up forming an excess oxygen to form or to produce. Let's try to stay away from the language of forming because that sounds like formation. To produce, we're going to produce carbon dioxide, and water. Right. So pretty much very similar to what we did. We do guarantee that we have complete combustion, but probably the new bit here is we're only going to be balancing it with 1 mole so that I can scale it up later on. Just while I'm at it here, if this weren't the case, if we weren't complete combustion, if say we were partial combustion instead, So if there wasn't enough oxygen here, if the fire was just starting to get started, instead of getting the full CO2, the fully oxidized form of carbon, you tend to produce Cs and carbon monoxides. Carbon would sort of look to us as sort of dark soot that comes off the flame, so it gives rise to a very dirty flame here. Carbon monoxide here is actually a poisonous gas here, so they really like asking that in a paper 1 question. During partial combustion, which of these are possible? Instead of the fully carbon dioxide that we expect, we sometimes do get Cs and COs. So, just like yesterday here, we're just going to practice writing a combustion reaction. So, this is not looking at delta H just yet. This just says, okay, I want to write the combustion reaction for ethane. Right. So again, if you're more familiar with organic here, eth means there's 2 carbons. The alkane ane ending means there's single bonds between those carbons. In this case here, it's going to be 2n plus 2. So given 2 carbons, 2 times 2 plus 2 means I have 6 hydrogens, or you can just draw that out. I want to see the burning reaction in this one. Yesterday we did exactly this molecule, but we were just comparing bond enthalpy formation. Today we'll actually do it as a full combustion reaction. So in yesterday's reaction here, when we balanced it, we started off with C2H6. We're going to find that the smaller alkanes, these ones here are actually gaseous at room temperature. You should be able to think about the intermolecular forces or London forces. They're relatively weak. We're going to burn them in oxygen. Oxygen comes to us diatomic. It's a gas. We're going to assume a complete combustion. So CO2, gas, water. Remember, 3 out of the 4 things, right? We always need oxygen as a reactant. We always assume complete, so we always get CO2 and water. That's why water tends to be really easy to predict. Just looking ahead later on here, when we then define the delta H for this reaction here, I will be delta H with that not symbol there. Just going to remind you from yesterday, that not symbol means I'm at standard state, standard conditions, so that I have a fair comparison. Some standard comparisons here would be, for example, 298 Kelvin, which is 25 degrees. That's different from chapter 1. Chapter 1, it was only 273, it was 0 degrees. So everywhere from chapter 2 onwards into grade 12, standard temperature is actually slightly hotter than room temperature, which is 25 degrees. 298 Kelvin, we have 1 bar worth of pressure, 100 kilopascals. We can have the most pure stable allotrope, 1 molar. Those are some of the factors that we talked about yesterday, and all that's hidden in just that little not symbol there. In this case here, because we are standard state, we're going to encounter these ones here in their regular conditions. So I mentioned this is a fairly light alkene here, gaseous, oxygen, gaseous, CO2, gas. It's a non-polar covalent compound here, so just London forces. Although when the fire is burning and it's really, really hot, it's true, water will actually start off as a vapor, but because we are going to be going back to standard state, I'm going to be waiting. When we expect water at 25 degrees at 1 bar worth of pressure, it's actually best to say this one here is liquid. So make sure you put water as a liquid for all these combustion reactions. This sort of assumes that the water had cooled down back when we're at standard state. Maybe we need to extrapolate back because the water is still gaseous at this point, but we were going to figure out here water as liquid. If you compare to yesterday's lesson here, you saw us put water as a gas. That was just so that I can make a comparison with bond enthalpies, but that was just purely for that question. From here on out, we're just going to use water as a liquid. So just watch out for that. Yesterday, as we were trying to balance, we noticed we had a problem. We ended up getting, 2 carbons should have been 2, 6 hydrogens, I need 3 times 2. I get an odd number of oxygens of 7, and unfortunately, it's not going to match with the even number. Yesterday, what we did is we said 2. Let's just double everything here. 2, 7, 4, 6. And everything was balanced, everything was good, everything was happy. This time, because we're defining it very technically as a combustion reaction, this time I will want to introduce that. Nope, when I balance it, I do want to burn only 1 mole. So just like a formation equation here, it's like trying to balance the thing that I did yesterday, but it's like having this one here. Nope, this one has to be a 1. So that when I get the enthalpy of combustion, this delta HC, it's burned for 1 mole, and therefore you can scale it up or down however you like later on. You might get the odd fraction. Because of that technical note, it has to be 1. We're okay with just leaving the fraction. It is a recipe after all. We're not getting 3.5 oxygen. It's just by ratio. For every 1 part C2H6, say 100 molecules of C2H6, I have a ratio of sort of 3.5 times more, so 350 O2 molecules. In this case here, I can run that reaction as fairly easily. If you have to guess, combustions are always exothermic. So combustions are always exothermic. they always involve, yeah, you're breaking a ton of bonds on this side here, but we tend to release more energy afterwards. Or you can say there's stronger bonds on this side here. We're ending up putting more energy on this side. So there's a net loss of energy as reactions become products. And in this case here, because we do have that 1 mole, I can now call this delta Hc value. I can call it the standard heat or standard enthalpy of combustion. Again, lots of definitions in this chapter here. Fortunately for us, a lot of it is very similar. So standard heat here, it's talking about enthalpy change. It's talking about delta H, talking about products minus reactants. Enthalpy change for, and as I mentioned yesterday, we did formation. I just wrote out the definition of formation. This time it's combustion. You can reread out the top. Burning 1 mole of your species into CO2 and water, right? So we are looking at the enthalpy change here, just like with the formation tables from yesterday. That was on table number 12. These combustion values are on table number 13. So let's just pull up to that for a second here. So this is the next page out of your data booklet here. If this were a paper 1 question where we don't get the full data booklet here, they might just use X's and Y's and just ask you to operate on the, oh, is it double X or minus Y, things like that. But in the case of paper 2, paper 3, you actually have a handful of chemicals here. You have the states that they are in standard state. That's what that not symbol means. And you'll notice here, like we said, combustion should always be exo. The delta H should always give you negative delta H. I should always end up in a more stable, low energy state as products. Some of them are only in the hundreds, some of them are upwards of thousands, but these are without actually writing out all the reactions, right? So we just did ethane here. I showed you the reaction of this guy burning, and then they actually give you the number. When you burn ethane, experimentally it was found to be negative 1561. They've done a similar reaction for all these other ones, burning all these other compounds. In fact, let me just make one note here. Let's imagine I was trying to burn hydrogen. What would the reaction look like if I were burning hydrogen? So that would be H2 is my chemical I'm burning. I have to burn only 1 mole, so that one there can't be changed. I burn in excess oxygen. I burn to produce O2. In this case here, while I'm tempted to say CO2 and water, I can't get any carbon source coming out because I didn't put in any carbon source. So in this case here, I actually only end up getting the water product. That's a 1 there. I would have actually normally rounded it sort of 2, 1, 2, but because this one has to be a pesky little 1, I'm going to take half of the oxygen here, and therefore I'm going to get 1 here. So this one here in words can be looked at the combustion of hydrogen. But if you think about yesterday's lesson here, if I also create 1 mole, there's another pesky little 1 there, I create 1 mole of my compound, and I start from the method of using the elements, this one here could also be called the formation of H2O. So because this one formula is given 2 different names, we're actually going to be able to match up here. The enthalpy of combustion for hydrogen is actually equal to the enthalpy of formation of water, give or take a little bit of rounding. We can find this one here currently on table number 13. If you match up table number 12, when I actually make water from the constituent elements here, it's the same reaction. So therefore, it has to be exactly the same energy change. In the past, they used to be really sneaky. They used to not give you the hydrogen and the carbon value. They used to rely on this relationship. Nowadays, they give it to you on both tables, which is nice. Sometimes people mistakenly think, oh, that's fine then. Combustion is always equal to formation. No, careful. There's a very technical note here. Yes, sometimes combustion of elements, right? If I burn the pure stable thing, combustion of elements usually is the formation of the oxide, right? So not just, oh, combustion of H2 is formation of H2. It's combustion of H2 ends up making the oxide form with hydrogen, which in this case here is water. And here also makes a note here. Yesterday we said elements are as simple as you can get. Formation of elements is always 0. In this case here, we have a bunch of elements here, and we see that the combustions are definitely not 0. When you burn elements, there definitely is a reaction involved. You're breaking bonds and forming some new ones. Combustion of elements here is not necessarily 0. There is one element, however, combustion of that element is 0. See if you can think about it there. What element, when I burn it with oxygen, would result in no reaction? Would result in, well, there's no equation, there's no change. I'm looking at a container full of this thing here anyways. Hopefully you're able to say to me here, plus oxygen, well, I'm going to form just oxygen. I don't want to have broken any bonds. if the chemical I were looking at were oxo-oxygen and it was just 1 mole of that there, that one there would be no reaction. So while the heat of combustion of elements in general tends not to be 0, right? We tend to get numbers like -286, 297, 394. You don't need to memorize those. The combustion of oxygen doesn't burn, so then we're going to end up with this actually being 0. So you also won't find combustion of oxygen because that implies that there's no reaction. Okay, so we introduced that sort of technical note here. What is a combustion reaction? Now, just like yesterday, we want to work back an enthalpy cycle so that in using these combustion numbers, we want to be able to figure out the delta H for any reaction. So, while you don't need to keep copying out the enthalpy cycle every time, I just want to prove to you where this formula is going to come from. So consider an enthalpy cycle. Consider me going from some generic reactants to some generic products. All right. So the questions in this section are usually, find the delta H of this equation. So this one here, I'm going to emphasize this is my big equation. I'm going to say this is delta H of any reaction. Could be decomposition, could be synthesis, could be redox, could be whatever. What we're going to do is we're going to engineer a detour. We're going to try to get from the same reactants to the same products without going the direct straight down path, but I'm going to construct a detour that involves combustion numbers. This time, like my enthalpy cycle from yesterday, instead of having elements sitting to the side here, I'm just going to have a bunch of burnt stuff sitting on the side here. What is my burnt stuff here? These are combustion products. These could be the CO2s and the waters I've been doing. If I burn things with, let's say, sulfurs and nitrogen, I might get SO2s and NO2s, things like that. But in general, I just have a bunch of burnt stuff here. If I just hypothetically, I'm not asking you to do this, but if I hypothetically take the reactants in the equation that you're interested in, if I imagine you burning all of those reactants, what's going to happen here is the enthalpy change for that reaction is going to be delta HC, is combustion, and because we're burning the guys on the reactant side, the heats of combustion on the reactant side. Let's go on the other side here, products. Similarly here, if I imagine I may have 3 products, doesn't matter, you're going to add them all up. Imagine pre-burning every single product, take 1 mole of that product, react it with excess oxygen, burn it all up, and we end up getting the heat of combustion for products. In comparison to yesterday's lesson here, yes, we had a similar enthalpy cycle, but you'll notice because burning is actually in this direction, we're going to actually, when we do our Hess's Law, we're going to have a slightly different sign. So here's what Hess's Law guarantees for me. Hess's Law says, as long as I have the same start, and as long as I'm going to the same finish, I can actually take this detour around, and it would also equally well give me my delta H. So again, I want to emphasize here, here's the equation we're going to work with. The delta H of any reaction that we're going to look at, I'm going to follow this detour. This time my reactant burning arrow is in the correct direction. So I'm going to sum up all the heats of combustion for the reactants. And I'm going to have to minus off, because I want to flip this arrow, I want to undo this one here. I want to minus off the sum of all the heats of combustion for your products. Again, that's another formula you do need to memorize. A lot of formulas here have the same structure. And again, just like I emphasized earlier, it just comes out from the enthalpy cycle. Sure, it turned out to be reactants minus products, but do be careful, the delta H is still starting at reactants, finishing here. It's still telling you, how does the enthalpy of products minus enthalpy of reactants? Are we overall endo? Are we overall exo? It's just when we use the numbers on table 13. These are heats of combustion data here. We just need to switch reactants minus products. I would just generally tell people, just always memorize everything is products minus reactants. There were only 2 times that it was actually reactants minus products. Before I show you an example of that here, bond enthalpy, I told you I would verify and solve that for you here. In the similar way here, if I have reactants and products, this time if they were gases and if they were averaged over, I can imagine bond enthalpying the reactants. I can imagine putting in the energy I need to rip apart all the bonds. This is why I said it's a little bit cheating here. I'm not exactly looking at bonds forming and how much energy is giving back. I'm actually also going to break up all the products. Here I have a bunch of broken stuff as well. So not burnt stuff, but I have broken stuff. Hess's Law again kicks in and says, if you want us to have the same start, same finish, I would follow the bond enthalpy, I would follow the reactants, but I had to flip the product arrow, which is why, again, the delta H of any reaction, but specifically it has to be gases at room temperature, the bond enthalpy form will look very similar. Bond enthalpy reactants minus bond enthalpy products. Right? Those are the only 2 times. It's going to be reactants minus products. We're going to see like 5 or 6 other formulas that are products minus reactants. So just remember, these are the 2 special times that it's actually reactants minus products. So let's just practice this here. I do want to emphasize the fact it's best if the equation that they're asking for is not currently a combustion when I'm going to try to use combustion numbers. So let me just show you an example of that, and then I'll show you in the last question what happens if it is. So here, I want you to determine the delta H for the following reaction here. I'm going to give you methanol, CH3OH. It's going to react with carbon monoxide. It's going to produce CHQ, so acetic acid, and we're interested in finding the delta H. We're interested in the delta H. Is it endo or exo? And we're interested in how much energy. That's the whole point of this chapter. I want to just emphasize here, this delta H, this big equation here, you will see this is not a burning reaction. It's not methanol with oxygen and pouring CO2 and water. This reaction has nothing to do with it. In fact, this one here may be just a synthesis reaction. So find the delta H of this synthesis reaction. What I'm going to choose to do, however, is I'm going to choose to use the combustion detour. I'm going to imagine somewhere behind the scenes, I have pre-burnt methanol, pre-burnt the CO and the acetic acid, and I compare the before and after. So here we go. The delta H, in this case here, my any reaction is synthesis. Let me just emphasize that. I actually have so far 5 different ways of finding delta H. I can use calorimetry, I can use formation numbers, Hess's law, and whatnot. This time what I'm going to do is I'm going to use combustion numbers. If you use combustion numbers, remember it's reactants minus products. Where did I get these combustion numbers here? As I mentioned, they're either given directly in the question or you can look up table number 13. So this means here, if I follow the combustion detour, imagine pre-burning the heat of combustion of methanol, add it to the heat of combustion for CO, right? So I'm not asking you to write out those reactions, but pretend to pre-burn those equations, minus off the burning hypothetical relationship of burning acetic acid, look up those values on the data booklet, and then we can actually go from there. So if you can have all your data booklets here, look up section 13. I pulled a very similar table here. For example, if I want to look up the burning value of methanol, I would look up methanol. Methanol is right here. Methanol is a liquid, negative 726. You can find the other values in a similar manner here. So this one here, I get a negative 726. If I actually showed you the reaction burning methanol, it's negative 726. The burning of carbon monoxide, same table. Double check my number, I was getting negative 283. Minus off the burning of acetic acid. Acetic acid, let me see if I can find it here. CHQ. Sometimes it takes a little while just to find which one it is. Acetic acid is called ethanoic acid, and I'm getting negative 874. Again, double check my numbers. So there we go. We had expected if I burnt these reactions here, everything is exo. So each of these numbers are negative. But this actually ended up forming for us the detour around. It got us from the same start to the same finish. So this will end up giving you the delta H, in this case here, of a synthesis reaction. Negative 726 minus 283, add a 874. I get a negative 135. The units are going to be kilojoules per mole because table 13 has enthalpies in kilojoules per mole. It's quoted per mole because technically we said burning 1 mole every time you run this statement once. Delta H being negative means it's exo. We know the heat turns on this side, and we know it's going to give off 135 kilojoules. It's understood per mole even if they don't write that in there. This one here could very well have come out as endo or exo. Doesn't really matter. It's just that we use the combustion way through it. The combustion numbers themselves are going to be negative. It's possible that this overall reaction was actually endothermic, and we'll be able to see that from the delta H that we calculated. So I'm going to give you one last question here. We're ready to be really confused. If you understand this one here, you'll be fine with these last 2 ways of finding delta H. What I want to find in this last question here is I want you to find the enthalpy of formation of glucose, really simple sugar here, C6H12O6. So just sort of in the symbols here, I would write here, I want delta HF of glucose C6H12O6. This time here, they're not giving you any expression. They're not giving you any equation. I want to come up with in what math or in what reaction would this term here actually pop up? There's actually two different ways it's going to come out. I'm going to show you both ways. You just need to choose one. Because I'm interested in doing a formation reaction, I can actually, when I derive my big equation, I can write a formation equation. I can show you what formation of glucose look like, write a formation equation. But when we actually go to actually solve for delta H, we're going to actually have to use combustion data, combustion numbers. And I'll show you why we can't use formation as well. So let's try it this way first. Formation of glucose means the making of 1 mole, there's a pesky little 1 there, C6H12O6, glucose is a sugar at room temperature here. Formation, out of all the ways I could have made glucose, I pretend to start off from the constituent elements, from the Lego pieces that build it up. I start off from plain old carbon, plain old hydrogen, and plain old oxygen. This would be solid, this would be gaseous. Because of that pesky little 1 there, when I balance it, I need 6 carbons, 6 times 2 for hydrogen, I need 6 oxygen, so no fractions, so be it. In this case here, my big equation happens to be, this is the formation equation. So if you found for me the delta H of this equation as written, that is formation. So the big equation I'm going to put on the left side. If I want to find formation, I still have 5 different ways of doing it. I can do calorimetry, I can do bond enthalpy, I can do Hess's law, I can do formation numbers, I can do combustion numbers. We now have 5 different ways of finding the delta H. Let me just show you what would happen if I try to use formation numbers as well. If I use formation numbers to try to solve this equation, I would end up having the expression, oh, easy. Take the heats of formation, it's going to be products minus reactants. Let me draw you one more step here. The products in this case here, the heat of formation for glucose, that's the one I'm looking for, is going to equal to the heat of formation for glucose. That one is my product. And I'm going to minus off the heat of formation, carbon, heat of formation for hydrogen, and the heat of formation for oxygen. Each of these heat of formations are quoted for 1 mole, so I do need to scale these up here. That one there is a 1, no problem. This one is 6 times carbon, so multiply that by 6. 6 hydrogens and 3 oxygens. The problem with if the reaction itself happens to be formation and trying to select the formation way of doing it is you're going to have an X equal to an X, no problem. We knew that elements can't be formed from anything simpler than it. These ones here all die to 0. So while you're going to have a true statement, the heat of formation of glucose is formation of glucose, all you can say then is, yes, X equals X. Right? It doesn't actually help give you the number. So just to prove to you here, if the equation that you've written, if the big equation happens to be formation, it's best not to use formation numbers. So choose one of the other ways. I have like 5 different ways. And in this case here, while combustion numbers actually provide a detour, I can actually try using combustion numbers. So let's try it out here. If I try to find, in this case here, my big equation is heat of formation for glucose. I'm just putting glue for glucose. If I use heat of combustion, remember the formula. Using this data here, the detour was reactants minus products. So to get from the very same reactants to products, the numbers are actually swapped around. So this time, I'm going to actually involve 6 times the burning value of carbon plus 6 times the burning value of hydrogen. Notice I'm not asking you to write out these equations. I imagine the table has already shown you all these ones here. And I minus off the 1 time the burning of glucose. This time, at least, we're not going to get X equals X. Because these ones here are heats of combustion, or enthalpies of combustion, these ones can be found in table 13. So again, double check my numbers here. 6 times carbon's value here. Carbon's value I'm getting is negative 394. I think it's 393.5 on the other table. 6 times the hydrogen is negative 286. Plus this one here is actually going to be 0. We talked about oxygen doesn't burn, so 3 times 0 is still going to be 0. We minus off the heat of combustion for glucose. I was interested in finding the formation of glucose. I didn't have that number, but I do have the burning number on table 13. This was negative 2803, and this one here gives us the value that we want. The big equation, which happened to be formation this time, 6 times 394 plus 6 times negative 286 plus 2803, I'm getting negative 1277. Again, units are going to be kilojoules per mole. If delta H is negative, we know XO. So they didn't give me an expression. I had to come up with an equation myself to try to find that delta H. Here's the last way it can show up. This term here, heat of formation, could also show up if I actually use formation data. but we just said you can't do formation on an actual big equation that's a formation. What if instead I actually wrote a combustion reaction? What if my big equation was a burning reaction? If the big equation is burning, in a similar manner, I don't want to use burning numbers to solve a burning. I can have a reaction that's written as burning, but I can use the formation way to solve it. You just need to choose one of these two ways. They probably wouldn't ask this question this way. So I could also write the combustion, write the burning of glucose, and use formation data. So I'm just going to start you off here and I'll let you try it out. Combustion of glucose, burn 1 mole of C6H12O6. Burning requires oxygen. We're going to complete combustion to CO2 and water. You're going to balance that there. I think this is 1,666. All right. So we had that burning reaction. This time, my big equation, this time the equation as written happens to be a combustion. So that goes on the left side. To find the delta H of anything, again, I want to emphasize you have those 5 different ways. Calorimetry, Hess's Law, bond enthalpy, whatnot. You don't want to choose the combustion way because you get X equals X. I could choose the formation pathway. To use formation numbers here, it was products minus reactants. Let me just sort of sketch this out for you, and then you can verify for yourself. We're not, again, we don't have the formation value for glucose, but you can find the combustion value for glucose on table 13. Formation values are all on table 12 here. And what we're going to get is we're going to get something like the heat of combustion for glucose, that's the one that we have already, is going to equal to, pretend I had a bunch of Lego blocks, pretend I make 6 times the heat of formation for CO2 plus 6 times the formation of water. Careful again to emphasize water is going to be in the liquid form. Don't use the gaseous number for steam. We're going to minus off 1 time the formation for glucose, and I'm going to add 6 times the formation for oxygen. Where does my term show up? Oh, right here. I don't have the heat of formation of glucose. This one here is going to be my X. That means I just have to have all these other numbers, just a little bit of algebra here, and you can solve for X. The number may not be an exact match of what we did earlier, but it should be fairly close to negative 1277. I'll let you solve through that, and you'll know you got the right answer if you get something close to negative 1277. Okay. There's more questions on the worksheet. If you have any questions, just let me know. Thanks, guys.